Good morning. This is my great pleasure and my honor to introduce the first invited speaker of this month, Matthew Libera. Matthew is a professor of material science and engineering within the Department of Chemical Engineering and Material Science at the Stevens Institute of Technology. As the founding director of the Stevens Laboratory for Multi-Scale Imaging, he oversees a premier multi-user facility specializing in electron, X-ray, and optical imaging. Professor Libera's distinguished academic pedigree includes a Bachelor in Sciences from Lafayette College and both a Science Master and a Science Doctorate from MIT. Throughout his career, he has held prestigious research positions in institutions such as IBM Almaden Research Center. A celebrated educator and researcher, he is a recipient of the Jess and Davis Award for Exemplary Research and the Alexander Humphreys Award for Outstanding Teaching. In today's presentation, Professor Libera will explore the complexities of tissue contacting implants using hip replacement as a primary case study. He will discuss the critical challenge of implant-related infections and highlight his ongoing research into soft matter and biomaterials, specifically how hydrogels and microgels can be engineered to resist infection while actively promoting tissue healing. Please join me in welcoming Professor Matthew Libera.
Let's get the technology working here. Thank you, Alberto, and others. It's really an honor and a privilege to be here. I've known about the old guard for a number of years, primarily by way of Mitch Erickson. He lives around the corner from me and keeps me updated from time to time. I'm going to talk about tissue contacting implants. And I work at Stevens Institute of Technology. We are often referred to as a West Coast university. We are on the west coast of the Hudson River. You can see an aerial view of Hoboken. It's a little bit dated now. I took this when I was flying into Newark Airport. I was pleased to hear the Frank Sinatra songs. Hoboken is the birth town of Frank Sinatra, and I walk by a Sinatra statue every morning on my walk from the train station up to my office. So a very appropriate welcome. So I'm going to talk about tissue contacting biomedical devices. I've got a few here with me. I know at home you can't see these things, but afterwards, if anybody wants to see them, you're more than welcome to. This is a femoral nail. It would go into your femur if you fractured your femur. I was on a consulting case once because one of these things broke while it was in somebody's body. This is a knee implant, probably for an oncology patient. This would go into their femur. And this is a hip implant, and I will talk quite a bit about this. But you can see the sorts of devices, just some examples here on the left. And these are common. You know, my mother has two hips. My father has a pacemaker. My wife has a port for chemotherapy. And I'm sure, particularly speaking to this audience, a number of you have tissue contacting biomedical devices, and probably at some point all of us will. The picture from Science magazine is actually very old. That's from 2002, but it gives an example. It's not a real person. This was synthesized. Gives a kind of an example of the breadth and depth of the sorts of devices that are used clinically to improve health. Let's see, there we go. And importantly, these things are used a lot, as I think we all know, and that use is increasing, partly because we're all getting older. And I can speak for myself that my body parts are falling apart. I've got a physical therapy appointment this afternoon at Atlantic Rehab over on Central Ave. Um, there are new devices that are being developed. You can see the man-machine interface there. Implants that are going in our brain. If you can see the hand, there's a little implant inside. These things are becoming very, very common in Scandinavian countries, carrying information about ourselves. And I've seen examples where handicapped folks, to assist them, they just wave this across a kind of like a card reader, and it would open doors and things like that. And then there in the bottom right, you see an example of something from regenerative medicine, tissue engineering, where in this case there's an ear, and the picture of the mouse there with the ear growing out of it comes from the mid 90s. That's called the Vacanti ear. The Vacantis were two clinicians in Massachusetts, and they made polymer scaffolds that were embedded in this mouse, and then it regrew cartilage and caused quite a stir in all the popular news articles up in the day, because these mutant mice were going to take over Boston. More recently, you can see that example at the bottom. That was made at Wake Forest University, and the ears being grown in a test tube. And so, this sort of technology has been around for quite some time. It still has not really reached commercialization for all sorts of reasons that I'm happy to elaborate on. But the future's coming, and so these devices will continue, seeing advances. Let me speak a little bit about hip replacements. They're very common, as I think we all appreciate. There was a lot of work that was done trying to find the right combination of materials and formats for it. The current generation of hips really gets dated back to this guy, John Charnley. He was a British clinician. You can see him holding his prototype implant. It has the common ball and stem sort of thing that we're used to. So you can see the ball and the socket that it would go into. He took advantage of some new materials at the time. So combine the small femoral ball with a molded plastic socket. One of the problems they had was wear and friction. And the UHMWPE stands for ultra high molecular weight polyethylene, which is really one of the key advances at the time. And I'm teaching a polymer physics class right now. So we just went through the lecture saying modern polymer physics started in the 1920s. And so I looked up when polyethylene was discovered. It was 1933. So, here's Charnley, not too much after that, using these relatively new materials. These were fixed in the body by glorified super glue. And you can see the effects. One of the kind of cool things about Charnley is that he had his own machine shop, and probably aren't too many clinicians today that are out machining their hip implants and then putting them into patients, but he was able to do that. And one of the things about the success is that a lot of other clinicians started doing this, and a number of companies, the companies today are the Zimmer Biomets, the Diffuse Synthes, the Stryker Orthopedics, and so on and so forth, which then led to commercialization and production, and then the continued evolution of these devices. So one of the things, and I'll give you a kind of a precursor to where I'm going, I'm going to talk about how materials fail. And as an engineer, a lot of advances in whatever field it might be move forward because something fails, and then the next best thing comes up to try to solve that problem. In no chronological order, let me just highlight some of the things that were done to improve hip implants since the late 50s to today. One was to improve on that ultra high molecular weight polyethylene. Now, typically it's irradiated to cross-link it to make it an even higher molecular weight, to make it more wear resistant. The wear is really important. If you think about wear debris, you don't want little particles of polymer in that joint as it moves. Matching the material modulus. So this is a really important thing in the sense that our bone, the modulus is a measure of how much something will bend. So something that has a high modulus doesn't bend very much. Something with a low modulus, like a rubber band, bends a lot. And in the case of a hip implant, this is a relatively high modulus material, and your bone in comparison has a much, much lower modulus. The reason why that's important is because when you put two materials together like that, it's the higher modulus material which bears most of the weight. So when you've got something like this in your body and you load it with your body weight, the implant is carrying most of that load. So there's this empirical law, you can see they're called Wolff's law, which basically said if bone is not being loaded, it will resorb away. And so one of the early modifications or evolutions was to try to use lower modulus materials, so we would be matching the modulus of the implant with the modulus of the bone. I'll say one more about that in just a minute. Another thing is using cementless hips. So in the beginning, these were just glued in place, and we still use cemented hips, basically glorified super glue. But a cementless hip is just, this would go into your femur. So think tube, and the femoral stem would go into your femur. And basically it's hammered down, and then with over time, bone will grow into it. You can't see it from online, and you can't see it far away, but the top of this is very rough. The inside of this knee is also very rough, intentionally made that way so that the bone cells will grow in and over time fix that in place. Another then, coming back to Wolff's law, is this idea of loading the hip implant. So those of you that are close up can see that the bottom of this implant is really smooth and shiny, and the top is rough. And that's so that the top of this will be bearing the load up here and not at the bottom, because if it's loaded at the bottom, then the bone at the top would resorb away, and this thing over time would start loosening and start causing problems. Fast forward to today, one of the big advances is to do 3D printing so that we can have, instead of a whole array of these things that are fit to some common sizes, that you could have an implant that's designed to fit specifically to your own body. And there are companies that are now in this business, and it's particularly appropriate for an elective surgery where you're going to have this. My understanding, it takes about 6 weeks with the information being passed to these companies, could make one designed specifically for you. So you can see a picture of an implant here, the rough part by the thumb of this person, the acetabular cup, it's called, rough on the back, so bone from your pelvis will grow into that. Here's the cup, the ball. The balls are different materials. Oftentimes now they're ceramic because they're hard and they don't wear very easily. It's hard to get good numbers of these things, but there's about 600,000 implants, hip implants annually in the United States. It's pretty impressive to see how this has evolved. Many people will be having the surgery in the morning and be home walking on that device that evening. And when I talk to clinicians about this and patients, it's remarkable to see the impact. And I imagine many people in this audience who've had any of these devices have had that sensation where the hip or the knee was just excruciatingly painful, bone on bone, and then this implant is put in, and it makes a remarkable impact on the quality of life. Hence, they're so popular. And so these devices, you saw, they go throughout the body. They're all meant to promote healing. And then we come to this, and for those of you who can't read the cartoon in the back, it says, I can't say I'm entirely pleased with my hip replacement. So that's kind of my segue into my main topic, which is sometimes these things fail. And, all those advances that I talked about were really made in response to different ways that these materials would fail over the past many decades. And it turns out now that in the case of things like hips and knees and a lot of other devices, because they've been so well engineered over all this time, the current main reason why they fail is because they become infected. And that's what I'll talk about, but I want to make sure I put this comment in because some of you may not feel too comfortable with what I'm about to say, and I just want you to be aware. If you haven't had one of these infections already and you've got a hip implant or a knee implant or anything like that, the odds of you getting infected at this point are probably pretty small. So I wouldn't worry about this too much. Most of these infections happen early after the surgeries, and you'll see more about that. All right, so why is it a problem? And you can see, importantly, these infection rates are relatively small. So in the case of a hip implant, it's about 1% of the implants devices that get infected. But any of these devices you see on the left that are in your body are susceptible to this problem. They get colonized by bacteria. They cause this infection. And one of the things that's really important, and I try to say this to as many people as possible, this is a big problem because there is really no solution. And there hasn't been a solution for a long time. And we're really trying to build awareness of this. Not much has changed for decades. And I'll say more about that as time goes on. And just as these implants have such a positive effect on people's well-being and quality of life, when they become infected, they have an extraordinarily negative effect because these are really hard to take care of. The reason why these infections are so difficult is because when the surfaces of these devices, whatever they might be, get colonized by bacteria, those bacteria develop into what's called a bacterial biofilm. If you don't brush your teeth for a few days, that stuff you feel in your mouth is a bacterial biofilm. A really rich one. It's probably got about 400 different species of bacteria in it. And people spend their careers studying that sort of stuff. There's all different types of bacterial biofilms. You can see, I won't go into any of these technical details, but there's something called the biofilm life cycle, where individual bacterial cells will colonize a surface. They will then reproduce and they'll grow into that stuff, which is cells and what are called polysaccharides that are kind of the slimy stuff you feel in your unbrushed mouth, until they grow into what's called a mature biofilm, at which point they'll kind of open up and emit daughter cells, they're called, who will then go off and colonize somewhere else. But the original biofilm stays in place. This concept is not really that old. It was first really introduced in the late 70s, early 80s, primarily by a group from Montana State University. They were doing a lot of research on Yellowstone Park. And so some of you might recognize this hot spring from the Old Faithful Geyser Basin. When I was putting this talk together, it was the Sunday, a couple Sundays ago, when it was snowing so hard. And this was the screensaver on my TV from Comcast. If you're up close, you can see, so I'm like, how timely is this? It's snowing and it was 14 degrees that day. That was actually not at Yellowstone Park. That was 14 degrees and snowing here. But what gives the color in those geyser basins are different types of bacteria that are interacting with the light. Biofilms are also a big problem in industry because they can grow pretty much anywhere. And so in heating pipes and heat exchangers, in your shower head, trust me, you've got lots of bacteria raining on you every morning when you take a shower. And trying to unclog pipes like the one you see here from a biofilm is a real challenge. I won't elaborate again on any of these details, but this is really to remind me to explain why these biofilms are so difficult. Because you think, well, hey, I've got an infection, I'll just take some antibiotics and this biofilm will disappear and I'll be healthy. There's lots of evidence that says when bacteria form as a biofilm, their properties really change. And so they become a lot less sensitive to antibiotics. And what this curve is showing, it comes from a guy named Phil Stewart's group at Montana State. If bacteria in their planktonic form, you can kill them pretty easy. If you grow those same bacteria so they form a biofilm, it takes thousands and thousands times more concentration of antibiotics to kill them. So much so that your body couldn't tolerate it. And that's really the key thing. So when one of these devices gets infected, sometimes the infections can be managed, but more often than not, to cure them, the device has to be removed. And you can imagine the case of something like a hip implant or a knee implant that's a traumatic thing because all of a sudden you're without a knee or a hip for weeks or months. How big is this problem? The box here on the right shows some examples of infection rates. Knees get infected about 4% of the time, hips about 1% of the time. I won't go through that whole list. Big traumatic injuries, battlefield injuries, car accidents, things like that are open and contaminated. Oftentimes in those situations, the question is not whether or not these devices will get infected, but what will they be infected with and how bad will that infection be? Now, on the left is a quick estimate, just to say for the case of prosthetic joint infections, hips and knees, prosthetic joints, that the cost roughly is over $2.5 billion a year just in the United States alone. So this is a big problem and a costly problem in many respects. I'm going to pause here and show a video. We run something at Stevens called the Stevens Conference on Bacteria-Material Interactions. We've run it every odd year since 2011, except 2021 when we had the pandemic. And twice, and most recently we had the 7th conference last June. We've taken that opportunity to make a video, interviewed some of the experts that were there. You'll see that I act as the MC, kind of to fill in some of the blanks, but it was really an honor to get some of these folks there. And I really want to highlight this woman you see in the bottom right. Her name is Dasha Koltunyuk. She speaks, and she is a patient who's suffering from this. So let me try to play this. I'm going to push this button, and if it works the way Joel tells me, I'm going to be able to sit down for 8 minutes and have a drink of water. Here.
Implant infections are a huge problem across medicine wherever implants are used. I work at an orthopedic hospital, one of the biggest in the world, and I am one of 4 full-time infectious disease doctors whose job is taking care of these implant infections.
This is a huge, huge problem that we have to handle. And it's not just here in New York, but it's all across the country. It's in rural America, it's in urban America, it's in all walks of life. Everybody's sort of impacted by the possibility of an implant infection.
Implant infection refers to the situation where bacteria colonize a tissue-contacting biomedical device like a hip implant or a knee implant, any sort of device that's implanted in the body. And those bacteria then develop into a bacterial biofilm, which are very resistant to antibiotics. About 1 in 100 hip replacements get infected. About 1 in 30 knee replacements get infected. Infection occurs in the mesh used in hernia repair about 1 in 25 times. As many as 1 in 5 tissue expanders used in breast reconstruction get infected.
An implant infection is a very, very serious complication. We focus on making implants for what are called revision surgeries, and we also focus on the oncological orthopedic space, so people that basically have bone cancer or soft tissue cancer. Our patient population gets infected to the tune of about 15 to 20% for most of our surgeries. And then certain specific surgeries, like a pelvic replacement surgery, can get infected about 50% of the time.
My main area of expertise is taking care of patients with cancer who also have infections, usually to reconstruct a body part after a cancer surgery, such as a mastectomy. A woman might undergo a breast reconstruction and have a breast implant placed as part of that reconstruction. And when an infection settles in on that, that's an implant-related infection. Also commonly, we might see orthopedic-related infections when people have bones or joints that are replaced as a result of cancer surgery.
I am 32 years old and I've had 8 surgeries on my right hip, which includes 3 hip replacements. This all started when I was 14 years old and was diagnosed with low-grade osteosarcoma in my right hip. That was treated with a partial hip replacement. A decade later, that had to be revised to a full hip replacement, which led to some further complications. And ultimately, they had to put hernia mesh in the area to secure some of the hardware. And ultimately, this got infected. In 2019, I walked down the aisle with a huge blister on the side of my thigh, which ultimately just exploded. And a week after my wedding day, I was in the hospital getting treated for my prosthetic joint infection.
The question of how devices get contaminated is really an ongoing, somewhat of a mystery, because the clinical outcome that we see is an infection, and we know when that happens. But that is so far removed from the actual contamination event that it's oftentimes very difficult to know.
Device contamination or device infections sometimes happen early because of the surgery. Let's say the bacteria gets in during the surgery, and sometimes they happen a little bit later, perhaps because of a delay in the wound healing. The skin hasn't closed all the way. And then sometimes you can get infections through the bloodstream, hematogenous infections.
The first time that the infection came, I didn't really understand what it meant. I knew it was bad news, but I didn't understand how bad. I thought an infection was something that could be treated with antibiotics and you go on. I didn't understand that it meant surgery, taking everything out, really painful procedures, really difficult drugs, a very long recovery process, being unable to work for a long time, an enormous toll on my family and my husband, on my parents.
If I had my wish, it would be to have material that by itself resists biofilm formation, but isn't itself a risk for infection.
So a lot of people think about the biofilm. We are trying to prevent the biofilm by killing the bacteria at the point of initial attachment to the biomaterial surface. So we do this by applying a covalent, non-eluting surface chemistry that mechanically can kill bacteria. And so the goal is to prevent the biofilm before it starts.
There's a lot of new technologies that can be developed. Having new ways of delivering therapeutics on demand when needed is something that's certainly achievable. Now, the question after that is how do you actually get this to patients? And I think that's the difficult thing.
I was aware that infections happened, but I didn't really understand what that meant. I think we're all familiar with, a strep throat. What I wasn't familiar with is that when you have an infection on hardware, it becomes something else entirely. It becomes its own kind of cancer in the sense that it's this invisible organism that's really hard to treat, that's really hard to detect, and really hard to manage.
It's not one person or one group can really overcome this big challenge, this big problem. You have to work with a regulation, industry, patient, doctors, researchers. So clearly you need all the moving parts being in the same room.
I constantly feel like I'm looking over my shoulder, waiting for the infection to reemerge, and constantly having to make very difficult medical decisions about how to treat it because there isn't a lot of information or options available.
There's many aspects to this issue that really need to be resolved. We really need to find a way to move research forward to engineer new implant coatings that prevent bacterial contamination and infection. We need new non-invasive ways to detect whether or not an implant is infected. The methods we use today are basically the same ones we used 100 years ago. And when there is an infection, we need to learn how to cure it. We need to find new ways to eliminate biofilms from implants. Scientists and doctors simply haven't been able to do that yet. These are very big challenges. But perhaps the biggest is this concern or problem of raising awareness across society to recognize this at a level that is comparable to the awareness that our society has about cancer. It's a significant but really underappreciated fact that the 5-year mortality rate associated with something like prosthetic joint infection, PJI, exceeds the 5-year mortality rate of breast cancer. That's a compelling statistic. All of us are well aware of the significance of breast cancer. I think relatively few people are aware of the significance of device-associated infection.
I think it's really important to not lose hope. I think it's hope that brings me to do this interview and to tell my story, because I hope that it can inspire people to do the work that we need to provide better outcomes for people like myself.
So we've had at this conference, we've always worked hard to get clinicians to come and speak. Some clinicians are more receptive than others. My experience is military clinicians answer my emails right away. Yes, sir. No, sir. And I appreciate that. Others, drag their feet a bit. It's really important to bring that perspective to the students, the research students, many of whom are working on problems where they don't really understand the long-term clinical thing that they're trying to solve because they're just getting started. I say that because in all those years, this was the first time we were able to bring a patient to speak to our group. And those of you that could hear it, I think would agree that's a pretty powerful story. In any case, that was posted on YouTube, I think back in October. This is not quite like a Taylor Swift video that would have 2 million hits already. I think it's been viewed about 500 times, but it would be really nice to know who's viewing it because there is not much information about this problem, and obviously people are suffering from it. I'll talk a little bit about the three things that we kind of highlighted there: prevent, detect, and cure. Prevent, can we put coatings on these surfaces, the implant surface, to prevent the colonization? Detect, are there new ways that we can somehow tell, have clinicians be able to diagnose these problems? And then importantly, if one of these infections does occur, again, we've got these biofilms. Are there ways that we can resolve this? So I'm just going to go into little snippets about each one of these things, kind of in reverse order. Cure. This is an example from a colleague named Dave Davies. You'll see at the end, we collaborate with Binghamton University quite a bit. And he is working on something that I think is a common theme, but he's been able to do it particularly well. The cartoon shows on the left the biofilm growing on some surface. And the idea, because these bacteria in the biofilm state are resistant to antibiotics, but in the planktonic state, floating around in your body, they are susceptible to antibiotics. Can we disperse them? And so he's found this dispersant, that little molecule at the bottom, cis-2-decanoic acid, or cis-DA for short. I'm not sure how it works magically, but it seems to work pretty well. And you can see the cartoon in the middle. It's called a dispersion inducer, so it breaks the biofilm apart. You can imagine in an industrial biofilm in one of those pipes, this would be a great thing because you could just inject it, disperse the biofilm, and now you've got flow again. But the idea is that in the body, you've now put these bacteria into the planktonic state. Green typically means live bacteria. And if you introduced an antibiotic at that point, you would expect that they'd be more susceptible and you'd kill the bacteria. And red indicates dead bacteria. It seems to work pretty darn well. The issue is concern about releasing bacteria through your body and before you kill them. So there's certainly ongoing work there. A second area is trying to diagnose whether or not a device is infected. This is a real challenge, and it's an important challenge because, as I think many of us have probably experienced, once a clinician knows what your problem is, then there's a prescribed course of action that they would take. But up until that point, there's a lot of uncertainty. Is it infected? Is the device just loosening, or what it might be? And it's much more difficult to come up with some sort of specific plan. The way these things are diagnosed right now is not really that reassuring. The chart on the right is basically a scoring system that was developed in what's called a consensus meeting, where about 400 clinicians, orthopedic surgeons who would do these prosthetic joint replacement surgeries, all kind of came up and voted on the criteria they would use based on the limited sorts of tests that are available to them now to say, yep, this one's infected. We think it's infected. We're sure it's not infected. And it seems kind of like a really crude way to do this. The note in the bottom left, there are some emerging sorts of DNA tests and enzyme-based tests that are being used to diagnose these infections. They're costly, they're slow, and they are not well accepted yet. So there's still work to do there. One of the things that I'm kind of excited about is a technology that a couple of my colleagues at Stevens are working on. I will say that if it's successful, it will have earth-shattering implications. It's far from that at this point. You can see this picture of, and you probably all have kind of experienced this, if you shine laser light into your finger, your whole finger glows. This is not a very powerful laser, so I can see my finger glowing, but I'm sure you can't. And the idea is, can we use that to get information about an infection? So I have a colleague whose name is Yuping Huang. He's a physicist. He speaks a different language entirely, and he's big into quantum stuff. And so we've heard a lot about quantum computing and so on and so forth. And what he's been able to do with his particular quantum approach is pick out from that big glowing finger that very, 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 very small signal of light, which is carrying information about whatever it hits inside the body. And so there's a huge background of noise. Your finger's glowing because the light is scattering inside your finger. And his technology is able to pick out that very small amount of light that's actually carrying important information. And a second colleague, Henry Du, who used to work right here at Bell Labs for a while, is using that light in a technique called Raman spectroscopy. So all those wiggles in the top right corner, what's important about those wiggles is that they carry information that says, whatever that light is hitting is detecting this or that or whatever. And kind of the cool thing is that blob on the bottom right is actually a chunk of chicken breast on a glass microscope slide, and in between the glass microscope slide and the chicken breast is a thin layer of something called alpha defensin. So alpha defensin is upregulated by bacteria in an infection. So in principle, if you had a swollen knee, I failed to point out that picture in the very beginning, a surgeon could go in, extract some of that, and if there's alpha defensin in there, then that would be a good indication that you've got an infection. So this technique was able to shine laser light through a centimeter of chicken breast, and then it goes back and gets detected, and they were able to detect the alpha defensin. So, if we fantasize about where this technology might go, and this is not an unrealistic fantasy, we've got a picture of an MRI system, and we're calling this QRI for quantum Raman imaging. But the idea is that we would have a non-invasive technique, just like an MRI. A laser would be scanning your suspected infection. It would give you chemically sensitive information, which could say, yep, you've got bacteria or not. And ideally, it would say, not only do you have bacteria, but you've got this specific strain of bacteria, which would then inform treatment. And because the laser can be scanned, it would give you spatially resolved information. It's this part of your implant that is infected. So it's got some really intriguing possibilities. The third of prevent, detect, and cure is prevent. That's really where my own focus is, and we're involved in trying to make coatings to put on surfaces. A lot of people say, well, why can't you just coat these things with antibiotics? There are some of these devices out there, and this is a picture of what's called bone cement. So in a cemented hip, that's what the cartoon on the left is saying, surgeons can mix in antibiotic into the cement, and it elutes out over time. It leaches out of the cement and delivers the antibiotic. It's an interesting story behind this because this is one of the few FDA-approved devices or components where antimicrobials are allowed to be put into the device. And the reason why this was started, the push really came in the late 90s because clinicians in the operating room would be mixing this stuff up, and they had no real algorithm for how much antimicrobial to put in. So the FDA actually went to the Stryker Orthopedics of the world, asking them to develop these technologies and standardize these products. So they work, and this curve is basically just talking about, measuring how much of this, in this case, it's gentamicin, I believe, vancomycin, is eluted from the cement over time. It's not a real perfect solution because you can see the curve goes up really quickly. That means a lot of stuff is coming out initially, and then it levels off over time. So there's a burst release, it's called, and then the rate falls down over time, which becomes a problem because there's a minimum concentration of antimicrobial that's required to kill bacteria. And after this burst release, you fall below that number. What's probably more important, though, is if only 1% of the hips get infected, then 99% of the people who have this sort of treatment are needlessly having antibiotics pumped into their body, which is not a good thing because the antibiotics will kill everything else that it can, and that becomes a real issue. So the sort of thing that we've been working on is what's called a self-defensive surface. So we're trying to make coatings where we can incorporate antibiotics into those coatings, but only deliver them if the surface is challenged by bacteria, if bacteria try to colonize those surfaces. And so you can see this cartoon in the top right. There's that kind of green layer, that's our coating. And we've got green bacteria that are floating around outside. If they don't touch the surface, if they don't colonize the surface, we're not really worried about them because the body can fight them and get rid of those bacteria. It's when they land on the surface and start growing on the surface where this is a problem. And the cartoon then shows that we've got a dead bacterium, and right under that bacterium, the coating has released its payload. There's been three main ways for doing this. The coating can degrade by enzymes that the bacteria produce. Bacteria, when they land on the surface and start to metabolize, they lower the pH with lactic acid and stuff like that, and coatings have been made which can respond to that. What we've learned in our group is that we've made systems where if a bacterium touches our coating, we can that by itself can trigger the release of the antimicrobial, and the antimicrobial is transferred from the coating to the bacterium and kills the bacterium. So it kind of works like this. We've got a hip implant that's rough. You can see the cartoon. We make these things called microgels. These microgels are microscopic. Human hair is about 70 micrometers in diameter. We're dealing with things that are about 10 micrometers or smaller. So each microgel is much, much, much smaller than a human hair. We make them out of a polymer which has a negative charge. So if we make the surface of our polymer positively charged, we can just dunk the implant into a colloidal solution of these things, and the negatively charged particles will decorate the surface. And once they're on that surface, we can dunk this into a second beaker that contains positively charged antibiotics. And those will infiltrate into the microgels, and they will be loaded there. And really the research part of this, and I'm getting close to the end, the research part of this is trying to learn how to manipulate those microgels to keep the antimicrobials there for as long as we might want them to be there, but still be triggered to release when the bacteria come. So I won't go into the details, but this is an example. The Petri dishes you see at the top, the arrows in the bottom right there point to a little titanium rod. It's about 1 millimeter in diameter and about 1 centimeter long. We're using those because ultimately we want to put these into a rat femur to do an in vivo experiment. Here we spray them with bacteria. The one on the left is untreated. It's just a titanium rod. We roll that sprayed that after it's contaminated onto the Petri dish, and each one of those little white spots corresponds to a bacterial colony. And then in the bottom left, it's what's called a scanning electron micrograph, really high magnification. You can see kind of the rough titanium, but all those little dots you see are bacteria that have grown. Meanwhile, on the right side, in the bottom right image, we see no bacteria. Those little blobs you see are the microgels we put on the surface with the antimicrobials in them. And in the Petri dish above, you see no white spots. So at least in this in vitro Petri dish level experiment, this technology seems to work pretty nicely. I'm going to say just a couple more things, like why have we not had a solution to this problem? Why aren't we finding these coatings used routinely on these implants and so on and so forth? Typically, this shows the medical device translational pipeline. So really at the apex is the clinical need. We've got patients who need these devices. Typically, in response to that, we've got university research groups like mine or others, or small startup companies who would be coming up with some sort of technological solution. And oftentimes for some non-clinical problem, once those solutions are developed, oftentimes industry would pick that up. They'd buy these companies or whatever. For biomedical devices, there's a very large hurdle that we have to overcome, and that is we need to get regulatory approval. And so companies like Stryker Orthopedics, Zimmer Biomet, the big device manufacturing companies want their risk minimized when they buy these small companies. They want a device that works, that's been approved, and because there's so much expense involved. And it's a real issue. So this cartoon says, I suppose I'll be the one to mention the elephant in the room, with the picture of the elephant. This is really what has hindered us for a long, long time, because if we make a coating on a hip implant, and there are thousands of candidate coatings, thousands, people have been working on this for a long time, but to do a clinical trial that would say, yep, this coating is going to resist infection, we need something like 200 patients. More is better because we would get better statistics. But in the case of something like a knee implant, or a hip implant, I'm sorry, where the infection rate is 1%, that means our clinical trial has to have 20,000 patients in it in order to get the 200 that we need to actually say something good or bad about this coating. And that is just a huge burden on anyone trying to do this. And that has been the elephant in the room for decades at this point. There is some light at the end of the tunnel. You can see the stop sign right there, regulatory approval. What I don't show here on this one, but I did on the previous one, beyond the regulatory approval, there's another step which we haven't really confronted too much in this business. That is trying to get an insurance code that would authorize clinicians to actually get reimbursed for all this stuff. So it'll be interesting to see how the health insurers deal with these sorts of technologies as they come out. One of the things that is happening is, and this is great news, instead of saying this device is infection resisting, which is very difficult to show, there's been some recent advances saying, well, we can prove that it still promotes healing, but it resists colonization in a Petri dish. And so you may remember this image from the video. This is a guy named Jordan Katz. Lives in Millburn. He works for a company called Orthobond, which was a spin out from Princeton about 20 years ago. They've started making coatings for devices. Took them about 5 years to go through the regulatory process with the FDA to get their coating approved. They stake the entire company's future on this one device. And on the left, you see these so-called pedicle screws. They're used in spine surgeries, coated and uncoated. So these don't make infection claims. They make colonization resistance claims. From my point of view, when I need one of these things, I'm going to take one that's got a coating that claims in colonization resistance because, all things considered, that's going to make these better. They did this in collaboration with a company called Onkos. Onkos Surgical is right near Route 10 in Parsippany. Onkos, this is Gene Cleach, a Stevens alum, who was also in the video. Most of their products are for oncology patients. And you saw the video with the woman Dasha, an oncology patient. These are, can be really difficult sorts of things. So this is a really exciting development. And those of you that can read it, says Orthobond wins FDA de novo approval. So de novo is the strongest FDA approval that you can get and the most arduous process. So I typically finish my talks with this slide. It refers more to the prevent part of all this, the biomaterials part of it. It's really been interesting in my career to watch how this field has evolved. I didn't get really interested in infection until the late 90s, early 2000s sort of time frame. But people have been sticking synthetic materials in the body for millennia. And then it kind of became an engineering science in the 50s and 60s and 70s. And for a long time, and the body always reacts in some fashion to anything you stick in it. For a long time, the idea was, well, let's put coatings on there that will make these things invisible, inert, so the body won't have a response. This is separate from the infection problems. And all these different coatings were tried. And they all fail. The body always makes some sort of response. And what's really kind of cool about this is starting about 1990, the whole paradigm changed. And the paradigm changed so that let's proactively try to signal what the body does and how the body responds. And over the past few decades, it's been really astonishing to see what scientists and engineers have been able to do to biomedical devices to tune how they interact with the body. And one of the important fields right now is called immunomodulatory biomaterials, where signals are being put in to actively signal your immune system to help combat certain things and so on and so forth. all that's great. And there was a big paradigm shift around 1990. I think now we're starting to get to the point where there might be another paradigm shift. So we're not just talking about healing, which has been the paradigm. It's healing while simultaneously trying to minimize infection. With that, let me show my final slide, which is a thank you slide. I've been blessed to have some funding to keep this going. And importantly, this map at the top highlights a multi-institutional collaboration funded by the National Science Foundation. Stevens is the lead of this group. We collaborate with Binghamton University. They have a lot of expertise in bacterial biofilms. Syracuse University, there's computational chemists that we collaborate with. City College of New York, they've got a lot of expertise in translational medicine. How do you commercialize these things? And a leading vet at the UPenn Vet School, which is about 20 miles west of Philadelphia, right near Longwood Gardens, if that means anything to anybody out there. What a great place to work. This guy works basically at a glorified horse farm. He's a vet who specializes in animal models of infection. It's been a real pleasure to be invited, an honor. I really appreciate the opportunity to meet you all, and thank you all for your attention. I'll be happy to take questions.
Thank you, Dr. Libera. I think now we can say that our joints are in good hands. So will you take a few questions?
Absolutely.
Okay, everybody.
Thank you.
Thanks, I was up first. Thank you so much. This is a fabulous talk. I think a lot of us have had implants. How many people have had either a hip or a knee replacement? You know, I was one of the first of this group because I had a double hip replacement done in about 17 years ago by Tom Skolko at the hospital for special surgery. It went extraordinarily well. I've had no complications. You know, it's like brand new hips and it's fabulous. But the one thing that I was told, absolutely, whenever I have any work done on my teeth, I have to take antibiotics, a heavy dose of amoxicillin just before I go, and even for cleaning. So that's what I do. It always seemed peculiar to me that years later I could still get infections. And now I understand all of that. And thank you for that.
I will comment on the amoxicillin thing. I think this is my understanding, and again, I'm not a clinician. The concern there is when you get your teeth cleaned, you know, you open up pathways in your bloodstream. Oftentimes, you know, you see blood when they really clean you well. And like I said, there's a lot of bacteria in your mouth. So the concern is that bacteria would then get into your bloodstream and ultimately find their way to your implant. My understanding is the jury's really out on whether this is necessary or not. So whoever asked that question, wherever you went, you might go back and challenge your dentist or your orthopedist. They're very conservative. Same thing at the FDA, and that's one of the reasons why the elephant is still in the room.
Matt, thank you very much. For 3 months until an hour ago, I was extremely enthusiastic about the knuckle replacement I'm getting Friday. And I'm wondering if you have any experience with knuckle replacements.
I have no experience with knuckle replacements, but all the things I said would apply to knuckles and knees and hips and anything else. So do the physical therapy, get a good night's sleep the night before, and tell the doctor to wash his hands before. That sounds funny, but it, one of the things that, in addition to what we try to do, one of the important things that the field has evolved is trying to manage a surgical suite much more than in the past. I can ramble on about that a lot. One of the concerns, and there's a lot of clinical, opinion, because it's very difficult to prove, but one of the concerns is that the contamination often happens in the operating room. And there's lots of reasons why that might happen, but an operating room is not perfectly sterile. They're a lot more sterile than the environment we are in.
So a lot of people here you saw have had replacements. So let's say your replacement shows signs of wearing out. In the light of the things you've said, it sounds as though one should be very cautious about having a second replacement. And I wonder if you'd like to comment on that. Do surgeons advise their patients about the things that you have explained? Thank you.
Surgeons increasingly advise their patients about infection. Whether or not they really make it clear what the implications potentially are is a different question. But I don't think you can go into any surgery at this point without some sort of disclaimer that infection is a possibility. In the case of most orthopedic implants, like hips and knees, in my experience and understanding, they rarely wear out. Unless you're a 40-year-old professional athlete who is drawing a blank on the tennis player, the Scottish British guy, Andy Murray, thank you, who had one of these things and went back and started playing tennis. He's at risk of having to have one of these things replaced. And it's difficult because if you think about this rough surface, I should have passed this around. If you've got bone grown in there, it's really difficult to take it out. So the point of having that revision surgery is that's the sort of question you should have with your clinician. But the risk of an infection is not necessarily higher unless you've already had an infection. So if you've had an infected implant and you go through the revision surgery and all the therapy associated with that, the odds of having it reinfect are much higher than 1%, probably more like 10 to 20%. But if you've had a clean situation, in that unlikely event that you need to have it replaced, I don't think the infection concern is any greater than the original one.
If you don't mind, we'll take a question on Zoom. Phil, do you want to?
Yeah, thanks very much, Dr. Libera. Appreciate your talk. My daughter, both my daughter and I have been to Stevens. Both got 2 degrees there. She's biomedical engineering, working for Cordis with inserts and things like that. So somewhat involved with it. And I've been watching your biannual session there. The question I have is the preoperative rigorous cleaning and disinfecting we do, triple showering with the hydrogels and all that, and then swabbing immediately before would tend to give you some sense of confidence that, okay, at least my skin is clean and, we're going in fairly clean. So has work been done to determine what the infections actually are and where the sources of those bacteria could be? In other words, relating back to skin bacteria or something present in the environment, the operating room environment.
A good question, and we're glad to hear you and your daughter are Stevens alums. We want to have as much impact everywhere as possible. So the cleaning routines that we all go through are obviously very important. You can't over clean. Many of these devices, though, still get infected with bacteria associated with your skin. So hips and knees, the primary culprit is a form of Staphylococci, Staph aureus or Staph epidermidis. Staph aureus tends to grow in your nose. Some of you may have heard of MRSA, that's methicillin-resistant Staph aureus, or Staph epidermidis. Epidermidis grows on your skin. Even when you do all that washing and so on and so forth, there's still bacteria that aren't taken off. They're in your skin. And, if the device, when it's implanted, brushes up against your skin, that's a way to get the contamination. Another thing that we'd like to see, and I've heard clinicians complain about this, but it's hospital policy. It costs, at least a few years ago, about $100 a minute to be in an operating room. So if someone needs an implant, oftentimes if they don't have a 3D printed, customized implant, all the sterile packaging will be opened, and these devices and the screws and the tools will be put on the side in the back of the room so that they're all ready when the surgeon needs them and they can minimize the time in the operating room. But for that 10 or 15 or 20 minutes or 30 minutes or whatever it might be, there are bacteria that are raining down at, a number of hundreds per hour, but it only takes one bacterium to cause a problem in principle, because that one bacterium will turn into 2, then 4, then 8, and so on and so forth. So the short answer to your question is yes, there is some evidence of where these things come from. Oftentimes they're cultured. When you're doing cultures to try to determine what the culprit is, oftentimes it's hard to identify, does the culture actually come from the infection in your body, or was it some external contamination you brushed up against the skin when you're collecting the specimens? It's a complex problem, but and to solve it is going to take coatings and detection technologies and cure technologies, but also enhanced clinical practice, and the patient practice of washing is really important. I will say on that, it reminds me of another quick thing. I spent quite a number of years visiting Hackensack University Medical Center so I could listen to their monthly meetings on infection control. And the head pathologist there, who kind of ran those meetings, was an infectious disease doc, and he wouldn't shake your hand. He would just give you one of these kind of elbow things, and he'd use a handkerchief or a paper towel to open doorknobs, and but it's made me really sensitive to that sort of thing. I mean, I wash my hands a lot. When I go to a men's room, after I wash my hands, especially in the hospital, I'll open the doorknob with my paper towel, and then I'll hold it open with my foot just to try to minimize the amount of bacteria. And I say especially in the hospital, because think about, in a hospital, they're doing everything they can to clean the place. And so whatever bacteria are still present, they've resisted Clorox and Lysol and all that stuff. So they are the nastiest ones.
Thank you. My question has to do with cochlear implants, where they drill a hole in your head and put the thing inside. Is there anything different about that you could say?
Cochlear implants are increasing. They are important. I think at the third Stevens conference, we had a doc from New York who specialized in cochlear implants. There was a group, in fact, I think the name of the company is called Cochlear Inc. They're an Australian company, and they were one of the more vocal companies who was actually working in the area of trying to minimize infections. The good news is that they don't get infected very often, less than 1%. The bad news is when they get infected, it means a brain surgery. And, this guy specialized in pediatric problems. And so it was particularly difficult for children because the implant would have to come out, they'd have to cure the infection and so on and so forth. And at this time when children were learning how to speak, they did not have the auditory sorts of capabilities. So it was kind of a double whammy.
So just like Paul, Tom Skulko did double hip surgery, hip replacement for me in 1997. I was 57 years old. And fast forward to about 2015, I started to get a fluid buildup in my left hip. And it was aspirated at HSS, and it was 3 years, I think, of each year getting that fluid aspirated. They never told me it was infected. Also, I might mention that I was also advised to take antibiotics every time I went to the dentist. And so in 2018, Tom Skulko did a hip revision on that left hip that was giving me the problem, and everything was fine. And about a year or two later, 2020, my right hip needed to be revised with a longer hip implant and actually rings around the bone to keep it firm. I've been fine ever since. My last dental appointment, we checked, did I need the antibiotic again? We called HSS and they said, no, you don't need it anymore. So that was from HSS. But one of my questions, in looking at the list you have of participants in your program, I didn't see HSS, and I was surprised at that. So I might ask you about that.
Yeah, so Hospital for Special, I'm going to touch this thing. HSS is the Hospital for Special Surgery. I'm sorry? HSS is the Hospital for Special Surgery. It's it's also a West Coast institution. It's on the west coast of the East River. So we do interact with them to some extent. The first clinician in that video is from the HSS, and we've interacted with him quite a bit, Andy Miller. We'd love to collaborate with them. One of our challenges has been, getting funding to support our activities, which I can ramble on for a very long time, but it hasn't been easy. And part of the challenge is that this is a very interdisciplinary sort of problem. You might remember from the video, there was an Asian colleague, Hongjun Wong, and he made the comment, well, they're clinicians, they're regulators, they're patients, there's insurers, there's manufacturers, there's scientists. And, all those groups are familiar with this problem. And for years, we've all been trying to work on this problem, but none of them have really converged is the buzzword right now. And the actual grant that we have with the 5 universities is what's called Growing Convergence Research, where we have these very different sorts of expertise that are all converging around a particular problem. So yeah, it's not a matter of would we like to do it? It's really finding a mechanism of how to do it most effectively. But I'm glad to hear that your situation is good. Good.
We have a few more questions, but let's try to keep the personal testimony to a minimum. Thank you.
Just before my question, I'm an implant specialist, Tom Mulligan. I've had just had a left knee done, and I've had a hip revision. The story is that my hip was done in 2017, 2016, about a few years later, I was told, no, excuse me, the hip was done in 2011. I was told in about 2017 that the hip had been recalled 6 months after I had it put in, but I was never told about it. So it did a lot of damage in there. I had to go to HSS for a hip revision. And I'm just wondering, in a situation like that, who should have told me that the hip had been recalled? It was a Stryker hip. They did set up a compensation fund, but I was so late in applying that I didn't manage to get anything.
Well, that's an interesting testimonial, and I appreciate the testimonials. One of the things that we don't get enough of is understanding what the patient perspective is. So thank you for all of you who've shared that. My short answer is I don't really know. But I brought my car to the Subaru dealership in Morristown last week, and they said well, there was a recall on this 5 years ago, and so I got it fixed, but it's more challenging in a case like yours because as time goes on, then it gets embedded in your body even more.
Quick question. So what percent of these infection cases you've been looking at morph into like full-blown sepsis?
So the question is, which fraction of these cases morph into full-blown sepsis? So sepsis is when you get a bloodstream infection, and that is ultimately what would lead to death if it's not controlled. That's probably in these cases which ultimately end in mortality. You saw the graph on the video. The 5-year mortality rate for PJI is higher than the 5-year mortality rate for breast cancer, and that's pretty startling. There are a lot more breast cancer cases than PJI, but ultimately it's the infection which likely ends up killing you, and it's not because of it being localized here. It's because it's spread throughout your body. Yeah.
2 questions. From the pharmaceutical company perspective, which I work for, I can't imagine a company going near this in terms of biosurface for a number of reasons. Antibiotics is largely a dormant field. 2, the size of the clinical trial, I would guess, would cost you $200 to $300 million to do it. And the third reason is the product liability issues that you'd face. So I wonder if that jives with your impression. And the second question is pretty straightforward. You indicate there's a 4 times significance of infection with knee implants than hip implants? Is that the surface level, the mobility of the joint, or what exactly is the reason for that?
All right, you're testing me that I have to remember two questions. So the first question had to deal with liability and things like that. And let me just make a comment because it's important for all of us. The antibiotic pipeline, so he talked about the pharmaceutical companies. It used to be that the Mercks of the world and the Bristol Myers Squibbs all had big groups that were doing antibiotic development. They're gone. That business is almost entirely dead because it costs so much money to develop these antibiotics. And very quickly, once they became used, the bacteria would be developed or bacteria would evolve that would be resistant to those antibiotics. So these companies could never get a return on their investment. It's something that as a society, we really, really need to worry about because these bugs are getting worse and worse as time goes forward. You were right about the clinical trial costing too much, and that's the reason why folks just have not been able to do these sorts of things. In terms of product liability, I think that what we will see in response to your question, I think that until I think we'll see these sorts of technologies emerge in the situations where infection is most common, where the numbers are high, and it will have the biggest impact. The other example where these coatings have been put on, they can't make claims of infection resistance. They can make claims of bacteria don't stick to these surfaces. What we will see over time is these companies have to follow how these devices are used and the outcomes. So we will start getting some so-called real-world evidence over the coming years of how many of these get infected versus uncoated ones. And I think what we'll see long-term is claims of infection resistance, not because of a clinical trial, but because these devices will show that they ultimately minimize infection or reduce the infection rate. Knee implants, thank you. I would have gotten there, but it would have taken me a while. So knee implants do get infected more frequently than hip implants. My understanding is that's because the blood supply to your knee is much less, and so it's the blood which really makes an important difference in terms of carrying things to and from these surgical sites. And same is true of other extremities. One of the things that has always baffled me, and it's a little bit of a morph of your question, is why don't these implants get infected more often?
I've learned not to touch the microphone. This is okay. My question has to do with symptoms should an infection be developing. We have appliances in our bodies in case a leg has been broken and that was needed to repair it, and many joint replacements. What are the typical range of symptoms that we might see? And for instance, with some of these procedures, there's good days and bad days when there might be no pain and when there is pain. And is this an indication of any beginning infection?
That's a really good question, and it kind of gets back to the one of the points in the area of detect that it's hard to diagnose these infections. But I again, not being a clinician, if you see swelling, if you see persistent swelling, persistent redness, those are signs of inflammation. But oftentimes, by the time the docs say, "Yep, it's infected," it's a pretty full-blown infection, and that's why something like this QRI technology, if it could be developed, wouldn't it be great? Just a routine thing. 2 weeks after your surgery, you go in that little box, it scans you and says, "Yep, you're clean," and something like that would have a really big impact.
We have one question from the chat box. What about stents? Are they vulnerable to infection?
So the online question is, what about stents? So stents are used to expand coronary arteries to get blood flow to your heart. It's a great question. I spent some time early on learning about stents, and there's cool engineering associated with this tiny little thing that then expands into this really big thing. From a metallurgical engineering point of view, it's remarkable. They don't get infected very often, again, because of blood flow. They're put into a situation where you've got rapid blood flow going across them, and so it's very difficult for bacteria to colonize those surfaces. So, stents suffer from all sorts of other issues that you have to worry about. Where infection, coronary issues are a bit of a problem in your heart. And I've got all sorts of heart issues I'm learning. I just got an Apple Watch, so it will take real-time data on my pulse. But if your heart isn't fully functioning, so that eddies form, behind the heart valves, that's places. I mean, it makes sense, that bacteria could accumulate there, just like, in a river, if there's a cove and there's eddy, you see trash that tends to accumulate in those places. But stents are pretty resistant to colonization because of the rapid blood flow that they see.
Well, thank you so much, Matt. That was a class A presentation.
I'm sure you guys say that to everybody.
Yeah. Well, not always, but we are very appreciative that you really accepted the invite to give us a talk.
Well, it's important to know that my wife and Alberto's wife are really good friends. So I couldn't really say no.
Well, thank you. We have two forms of giving our thanks to you. One is this appreciation that has this logo with the orchid. Perhaps you know that Summit was the capital of the orchid in the 30s.
I did not know that.
Which is why we put this logo there. And the second is the salute from Old Guard. Thank you so much.
Thank you all. I really appreciate your time, your attention, and happy to talk to anyone.